Hello, welcome to another lesson in geometry. Today we are covering section 2.1, patterns in inductive reasoning. So inductive reasoning, real fast we should probably write a definition for this, is reasoning based on observable patterns. So what have we seen? For instance, if precipitation is coming down and the temperature is 0 degrees, I'm going to say that precipitation is going to be either snow or ice. Okay, and I've observed that through my life because every time it's really cold and something falls from the sky, it's not rain or hail, it's usually snow and ice. Well, it's always snow and ice. Okay, all right. So our vocabulary for today. So tell whether each statement is a conjecture. So first off, conjecture, what is that? A conjecture is a conclusion based on inductive reasoning. Okay. All right, so that means the thing that we have observed, the patterns we've observed, always are true. We keep seeing it happen over and over again, so we can conclude that that's a conjecture. Okay. Our first one, is this a conjecture? All apples are sweet. So throughout life of you eating apples, have they always been sweet? And I'm going to say no. This is not a conjecture. It's not a conjecture I would make. This is not a conjecture. And that's because I've eaten unsweet apples before. Okay. You might even say I've eaten apples that are meant to be unsweet. Some apples, like Granny Smith apples, are meant to be tart. Okay. Or you might just get an apple that doesn't taste right. Okay. So my observable facts about this is that not all apples are sweet. All right. So the sun sets in the west. Is this a conjecture? This is yes. I have always observed the sun setting in the west. Okay, I've been around a lot of places in the world, and every place I've been, the sun's always set in the west. Okay, all right. So a couple vocabulary things. Reason. Okay, words. Reasonable is an adjective. Reasonably is an adverb. So a definition here: a reason is an explanation for something. Okay. The earth rotates around, so the sun always sets in the same place. That's my reasoning for why that conjecture above was true. It's also a logical argument, uses reasons to arrive at a conclusion. All right, use your vocabulary now. Complete each statement with the appropriate word form of the word reason. In a logical argument, you state each reason. That's the noun form. So each reason, so we do a bunch of reasons. We think this reason, this reason, this reason. That's why that's my argument. Okay. All right. An adjective form. The student did a reasonable job on the last math test. Okay. So that explains the type of job they did. They did okay, reasonable job. All right. Adverb. The workers clean up reasonably well. That means they do pretty well. Okay. Notice it's changing the verb well in this case. To make a good decision, we reason together. That's the verb form of reason. This is what we are doing, and this is a statement that helps us prove something. Okay, a little bit different. All right, so write R in the statement if it's reasonable, or U in the statement if it's unreasonable. So let's look at our first statement. Our first statement says 32 plus 11 plus 6 is about 60. Well, 32 plus 11 is 43, and 43 plus 6 is 49. I don't think I would estimate that to about 60. I'd estimate it to 50. So I would say this is an unreasonable statement. Okay, a 15% tip on $36 is $6. Okay, so to find out if that's reasonable, then I'm going to do 15%, I'll write it as a decimal, of $36. And let's see if that's about right. So 0.15 times 36 This will give you about 540. So a reasonably good tip on that, yeah, that's about right, $6, 540. You're probably not going to pull out 40 cents, you'll just round up to $6. So I think that's reasonable. All right, let's flip the page and see what's on the next side. Okay, so in this section, we are going to try to observe patterns in numbers and sequences and see if we can make a conjecture about other patterns and then use that conjecture to find answers for farther in the pattern without actually having to write it all out. Okay. All right, so let's start with finding and using a pattern, problem 1 here. What are the next two terms in this sequence? So the sequence starts at 45 and then goes 40, 30, 530. And if you look at it, it seems to be going down by 5. So I would say that the next two numbers are 25 and 20. Okay, they're multiples of 5 going downwards. Do the numbers increase or decrease? Well, okay, so these guys decrease. Okay. Does the amount of change vary or remain constant? So does it keep decreasing the same amount, the rate of change, how much it's going down each time, or does it keep decreasing a little more or a little less each time? And in this case, this is a constant rate of change. Okay. Which operation helps you form the next term? Okay, well, we're doing subtraction from the previous term, so it's going downwards. Okay. And which number helps you form the next term? And well, it's subtracting by how much? Well, we're subtracting 5 each time. So how do you find the next two terms in the sequence? Or now find the next two terms in the sequence? And we've already done that above because we can use some common sense by looking at it. So this is the reasoning, the reasons to help us lead us to 25 and 20. All right, so we can make a conjecture about the next numbers. It will be 15, 10, etc. Okay. All right, so using inductive reasoning. What conjecture can you make about the 21st term in this sequence? It goes RWB, RWB, and we want to know what about the 21st term. So to help them, they make a table here. Now usually I'll put the number of term on the top and the letter in the sequence below, but they chose to do it the other way around. Or I'll make a T-chart and I'll say this is the term number and then here's the letter, and I'll say the first term number has a letter R. The second one is W. But theirs is fine. So the first term number 1 is R, the second one is W, and then we need to fill in the rest of the term numbers. So the third one is B, the fourth one is back to being R, the fifth one's back to being W, and the sixth one's back to being B. Okay? There are how many letters in the pattern before it starts repeating? Well, there are 3 letters, RWB, and then it goes RWB again. Those are called cycles, and we repeat the cycle over and over again. So there are 3 letters in the pattern before we get to a cycle. So R is the first term's letter. It's also the 4th one, and it would also be the next one, which would be the 7th. And then it would be the 10th and the 13th and so on. W is the second term. That's here. It also shows up on the 5th term, and would also show up on the 8th term. And B is the 3rd one, the 6th one, and so forth. Okay. All right, underline the correct words to complete the sentence. The 21st term is, let's see, is it 1 more than a multiple of 3? That's these guys. Is it 2 more than a multiple of 3? That's these guys. Or is it a multiple of 3? That's these guys. So the 21st, 3, 6, 9, 12, 15, 18, 21. Those are all multiples of 3. So the 21st is a multiple of 3. So make a conjecture. So my conjecture based on the first 6 observable facts are that when I get to the 21st one, I am going to get a B. Okay? And that's because I did this reasoning. Reasoning led me to that conjecture. So on the back side, problem 3, collecting information to make a conjecture. So what conjecture can you make about the sum of the first 30 odd numbers? So obviously we could just sit down and add up the first 30 odd numbers and find its sum. But what we want to do is make a conjecture that would help us not only to find that one, but all of them. So like maybe the first 70 odd numbers. And we wouldn't want to have to go back and do the first 70. Or if this said the first 300, we'd want to find a pattern instead of actually sitting and adding up 300 numbers. All right, so we're going to collect some information to help us reason about this problem. So what we're going to do is start with the easier ones. The sum of the term 1, which is just one odd number. Well, the sum of one odd number is 1, and then they rewrote this as 1 times 1. Okay, you can't really see why yet, but let's take a look later on and we'll see what was going on. All right, the second term is the sum of the first two odd numbers. So the first odd number is 1, the second one is 3. 1 plus 3 is 4, and then they're going to rewrite this as 2 times 2, another way to write 4. Okay. The third term is the sum of the first 3 odd numbers. So 1 plus 3 plus 5. 1 plus 3 plus 5 is 9. That's the sum of them. And I'm guessing that you can figure out that that should be found by doing 3 times 3. Okay. So they're saying, okay, well, let's check the fourth one. Okay. The fourth one would be 1 plus 3 plus 5 plus 7. If you add that up, that's the 9 from the previous one plus the 7 will make 16. Oh, I know what they want now. 16 is also a perfect square, so that's 4 times 4. So they didn't magically get this 1 times 1 to start with. What they did was they did a couple of these, and then they noticed a pattern here. And then their reasoning was, hey, look, we keep finding the perfect squares. So I bet you could get 5 without having to add them up. But let's do it anyways. 1, 3, 5, 7, 9. That's the first 5 odd numbers. It happens to add up to 25. And you could have found that 25 by doing 5 times 5 to start with. So if you want to know the sum of the first 30 odd numbers, my conjecture would be it's going to be 30 times 30, which is 900. All right. Problem 4, making a prediction. So we're going to look at some facts, and then we're going to reason about them to make a further prediction. Now, our facts aren't always going to work out exactly even, so just be careful. Sometimes we have to estimate a little bit. All right, so in real life, estimation happens all the time. What conjecture can you make about backpack sales in June? So over here we have a table. The number of backpacks were sold. Okay, so this is the number of them, and this is the month. And that's November, December, January, February, March, April. May's not on there, but we want to also know June even after that. Okay, so we're going to write true, false on some of these reasons here, and then they'll help us figure out a conjecture. So the graph shows a pattern of points. Oh yeah, that's true. Okay, there's definitely a pattern. It seems to be a nice downward trend here, right? Each month, the number of backpacks sold increases. Well, that's certainly not true. That's going downward. The trend is downwards. This is false. So our reasoning should be each month, the number of backpack sales decreases. All right, the change in sales varies from month to month, so you need to estimate this change. I'm going to say true here, but we can make some pretty good estimates because it doesn't vary very much. Okay. V-A-R-Y, V-E-R-Y. So it varies a little bit, but not a lot. If sales change by about 500, this is an estimate for how much they vary, you can subtract 500 from April sales to get May sales. And that's true. If we look over here, it starts at 11,000 and it goes to about 10,000, maybe 600, and then it goes down to about 10,250, but then it drops below to 9,480 or so, and then we're right around 9,000, then around 8,500. So they're up and down a little bit, but they're all about 500 down. Okay. So if sales drop by 500 each month, you can add 500 to May sales to get June sales. That's not true. It does drop by about 500 a month. That's the change, but it's not an upwards change. It's a downwards change. So this is a false statement. All right, but we can use that fact to help us. It's going down by about 500. So in April, it was about 8,500. So if we continue this pattern, in May, it'll be about 8,000. And in June, it'll be about 7,500. So about 7,500 backpacks will be sold in June. Okay, on our last page, we have one last problem, finding a counterexample. So a counterexample for a conjecture is something that would prove the conjecture not true. So we might have looked at some patterns and thought and use our inductive reasoning to come up with what we think is a true conjecture. And then somebody could come along and say, oh, nope, here's an example where it's not true. Okay. For example, maybe I observe that I think all 8th graders can tie their shoes because I've been teaching 8th graders for a very long time, and I've noticed everyone that I've ever seen can tie their shoes. And then somebody comes in and says, oh, no, nope, Johnny over here, he's always had Velcro shoes, and that's because he can't tie them. So that one counterexample would be Johnny, okay, the kid who can't tie shoes. All right, so what is a counterexample for a conjecture? This conjecture, if a flower is red, it is a rose. So a counterexample would be for us to find something that makes the hypothesis of this if-then statement true and the conclusion false. So can we think of a flower that is red and that flower is not a rose? All right, so circle below that are, circle the flowers below that are or could or can be red. I don't know what that's supposed to say, but I know what we're supposed to be doing is we're circling any flower that could be red. So I think a rose could be red. A bluebell, that's kind of common sense, that's not going to be red. I think carnations are pink and white and yellow, but I'm not sure. But I'm pretty sure geraniums are red and tulips can be red. So these can be red. They come in different colors, but they can be red. If every flower you name is a rose, no. So write a word to complete the counterexample. Let's see. So our counterexample for this conjecture is going to be a tulip is a red flower, but it is not a rose. All right. So what's this saying is, hey, here's my counterexample, tulips. Okay. All right. Okay, so in this notes, the lesson check comes at the end. So this is the part you should try yourself. And then that means pause the video now, go through it, see if you can do it, and then come back and check, okay? As opposed to the warm-up in the beginning. All right, so do you understand? Welcome back. Clay thinks the next term in the sequence 2, 4, and that's it, 2, 4, dot, 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 is 6. So here's the sequence Clay was given, and he says, I say the next answer is 6. That should be the next number. Ott, nice name, thinks the next term is 8. Okay? And Stacy looks at that pattern and says, no, 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 you're both wrong. The next term is 7. Okay? What conjecture is each person making? And then is there enough information to decide who's correct? All right, so choose a letter that best describes the rule for each sequence. Let's see. So 2, 4, 6, 8. That is a rule where we add 2 each time. Okay? That's part C. 2, 4, 8, 16. This is a rule where we're multiplying by 2 each time. That's choice A. 2, 4, 7, and then the next number is supposed to be 11 here. This is a rule where we're adding 1 extra each time, so that's choice B. Okay, you'll see a lot of typos in these book-made notes. All right, Clay's conjecture. Which one is Clay's conjecture? Well, Clay said it goes 2, 4, 6. That's add 2 each time. Ott's conjecture, which one is that? Ott said it goes 2, 4, 8. So that's choice A. We're multiplying by 2 each time. And Stacy's conjecture was 2, 4, 7. That's adding by 1 more each time, so that's choice B. So is there enough information to show the pattern, who's correct and who's not? And the answer here would be no. We need more numbers to see. All we really need is 1 more number and we can tell who did it right. But in this case, all 3 people have a conjecture, but it works for both of the 2 points in the, or 2 numbers in the sequence, but we can't tell who's correct until we see some more numbers in the pattern. So we need to observe some more facts before we're able to find a correct conjecture. All right? Okay, so the bottom one here you can fill in. Do you understand these vocabulary words? And then how well did you get the lesson? And if you're not able to check off all 3 of those words, or how did you get the lesson is like a 0 or 1 or 2, then you should go back and watch the lesson again. All right, I'll see you in class next time.